So we're going to go through that in just a minute. So here are the 3 lines. So check what you have. Get 3 lines on there. Do this right now. Okay? So you have these 3 lines. And then below it, it has some instructions for you. So if something's incorrect on your line, go ahead and fix it. Okay? And the directions below ask you to highlight the portion of the graph, meaning the line that you've graphed. Highlight on the line, okay? Each of these sections. And I put some highlighters out on the desk. It is not enough for anyone by any means, but if your whole group doesn't have one, okay, you also can just use a different color if you want or something like that. But there's a few back there if you want to share with your group. In graph number 1, you're going to highlight the portion of the graph, the line that you've drawn, that is in the domain where x is less than 1. So not that whole line has a domain of x is less than 1. This was actually in the summer packet. If we took the domain of the entire line, what would it be? All real numbers, okay? I only want you to highlight the part of it that would be in the domain where x is less than 1. On the second graph, okay, on the graph number 2, I want you to highlight the portion of the graph, the line that you've graphed, okay, that is in the domain where 1 is less than or equal to x is less than 4. So again, this line would have a domain of all real numbers. I only want you to highlight the portion of the graph, the portion of the line that falls in this domain. Okay? Same thing for graph number 3, but highlight the part where the domain is x is greater than or equal to 4. Okay? Talk with the people in your group so you guys can figure it out together. We'll go over it.
Just do the line to the graph.
You're highlighting on the line. Yeah. Okay, so first graph, okay, what does it mean for me to highlight on this line the part that's in the domain where x is greater than 1? Where should my highlighting be? Sorry, less than 1. Thank you. Yes. To the left of 1 on the line, and where the point has 1 as its x coordinate, right? So here's where x is equal to 1. Here's the point on the line that has that x coordinate. I want to then capture every point on this line that would have an x coordinate less than 1. Okay? So that is everything this direction. So on my line, that is all of these points. Okay? Now, right here at the end that I used as my boundary, I wanted everything on this side of it. That point that was right there is when x was exactly equal to 1. Is that included in the domain restriction listed on the bullet point? No. So what do we do when we want it to end here, but we don't want to include that exact point as part of it? Mathematically, what do we do? How do we note that? Good, a circle without filling it in. I want to come all the way up to this boundary, but I don't want to include it. Sorry, it's like super large. It's because I'm in like highlighter mode, okay? But so that's kind of the idea. I'm going up to that point, but not including it, okay? In the second graph, I want to highlight the portion of the graph that's in the domain where 1 is less than or equal to x is less than 4. So which part of this line am I highlighting? Yeah. Good. So where it's 1 to 4, and notice he pointed out on the x-axis, right? So 1, and then 2, 3, 4. Okay, so right in here. So I want to go from there to there. And then I have to look at what's going on. Okay, I know I want to highlight in here. Okay, I want to stop at the point on the line where the x-coordinate would be 1. That boundary point, do I want it to be something that is included as part of the points from this line? Or do I want it to be excluded? Like it's a boundary, but it's not part of what we can use. Included. And so I'm going to go ahead and that point forward. What about the other end point that's at the place where x is equal to 4? Excluded because it doesn't include it right here. Okay? So that part I would leave open. Okay. On the last line, I want to highlight the portion that's in the domain where x is greater than or equal to 4. Okay, so somebody tell me which part of the line am I highlighting? Yes?
You have to highlight from 4 and on 4 and all the way to the right.
Good. From 4 and to the right. So on the line, from 4 over, okay? And he made a note of it when he was saying it. Is 4 included? Yes, okay? So on that point and over to the right, okay, forever and ever and ever. So what we would then want to try and do, let me cheat a little bit. Sucky. Oh, it didn't get all my stuff right there. All right, well, you guys have it on your paper. My first one didn't copy, though you saw me copy and paste it. So, because it went on top of it. All right, so here's the thing. You want to now graph this function. Okay? This may seem very odd to you. This is one function. Okay? But how many pieces does the function have? 3. Okay? So we treat each piece like its own equation for a little bit because it has that part here. But notice it's all part of one equation. And then how do we make it so we don't just have 3 lines just running across the graph in their entirety? After each equation, we put a comma and we list the domain restriction. So instead of me putting a bullet point at the bottom and saying, only use graph 1 in the domain where x is less than 1, I don't write that. I just put a comma next to that branch and say x less than 1. That means you only use this graph during this portion of the domain. You only use this one in this portion. You only use this one in this portion. Okay? So basically, you could regraph all of these things only in certain portions of the graph. Or you can do what we just did. You can graph them all separately, and now you can just take the highlighted portions of them, because those are the only parts we want included, right? And put them all together to make one graph of what we call this piecewise function. Okay? So on this graph, you're going to go ahead and graph this function, which is the highlighted portion of each of the pieces you drew above. Okay? So go ahead and do that on your paper. So you're making one graph of one piecewise function using the information that we just highlighted. All right, so it should look something like this as you're putting it together. Okay? Sorry for my big point. I drew it open, but then I had to close it. Does anybody know why I drew it open and then I had to close it? As I was going through the process of creating the graph? What's that? Good. So, so they do meet, right? And so interesting ways to check this once we understand the idea. So here's the idea. Do you really want to graph all the different graphs by themselves every time, highlight and put it together? It's kind of a long process. But if you were stuck, could you do that every single time? Absolutely. Okay? Other thing you could do is you could put this graph on here and then just erase the part that you don't need. You could put the next graph on there, erase the parts you don't need, put the next graph on there, erase the parts you don't need. third thing you could do, especially useful when they're linear, this is what I did because my one got erased, right? I know that I want this graph until x is 1, and then I don't want it anymore. Meaning, when x is 1, I reach the boundary. So in my head, don't draw this on your graph because this isn't actually belonging there. But in my head, I kind of see a boundary line right here, right? And since this is a line and I know the slope, if you could just tell me where a point is on this line, it would be great. And specifically, I want the point where it hits this boundary because that's the stopping point. Okay? So how do I get the point from that line that is specifically on this boundary? What is the x value at the boundary? 1. How do you find a point on the line when you know the x value that you want to include is 1? Plug it in, right? Okay? So I just plugged 1 in here. 2 times 1 is 2 plus 1 is 3. Okay? So I knew this line would have the point 1, 3, but I made it open because I know I didn't technically want to include it. And then I drew a line with a slope of 2. Yes, I went down 2 and over negative 1, but I understood that's the same as going up 2 and over positive 1. Okay? So I could do the same thing here. Do they overlap? Well, plug 1 in here. When I plug that boundary point in here, negative 1/2 times 1 is negative 1/2, plus 7/2 is 6/2. 6/2 is really the same thing as 3. So this line also contains the point 1, 3. That's why I plotted that point there. And then I just went down 1 over 2. Or what I could have done is that one has a second boundary, right? I could have just come and plugged in 4. Okay? And then I would have negative 4 over 2 plus 7 over 2, which is 3 over 2, which is 1.5. So I know at 4, 1.5, and then I could have just connected the boundary points, right? I just have to know them when the boundary points are open and closed. Okay? That might not work with a parabola. If this was supposed to be a parabola in between there, I wouldn't know where it turned around and all that. But you could just plug in endpoints when it's just linear and we want to connect them. Okay? Is everybody all right with this? So you should understand that this is one equation of something we call a piecewise function. That if all else fails, you would literally take each piece and graph them separately, erase the parts you don't need or highlight the parts you do and then put them together on a new graph. Or you're going to use some of the strategies we just talked about. This is a boundary. I understand I could just plug in the point on the boundary to get the end point and draw the line in the direction that I need it to go in. Stuff like that. Okay? Does everybody understand that idea, okay, of how these work? All right, so let's fill in a couple things about this function. Okay? First of all, is this a function? I keep calling it a function. Think back to the definition of a function. Is it a function? A function means for every one input of x, you don't get more than one output of y. Or in other words, you guys do that vertical line test, right? When you do the vertical line test, you're saying if this is my one input of x, it's only supposed to have one output of y, meaning 1 point. If it has another point lined up with that x, then I have a problem. Does this pass the vertical line test? Yeah. So is this a function? Yes. Is this continuous? Meaning, if you start from the left of the graph and you trace it, essentially, and go to the right, do you ever need to pick your pencil up off of the graph? No. Okay? I could go like this. And go on forever in each of those directions. Now, I could have made this discontinuous. All I'd have to do is make this 2.5 instead of 1.5, right? And then this third branch of our graph, instead of being connected to this one, would have been right here. And that's totally okay. One of those endpoints would have been open most likely, and then one closed where the next branch started. They can be disconnected. So ours is continuous because we don't have to pick up our pencil. But these piecewise functions could very well be discontinuous. Yes? Yes. It will still be a function as long as, let's say we had this graph, right? But this branch makes the jump up here and then goes like this. If these are both filled in points at the same boundary, it's not a function because that one x has two different y coordinates lined up with it. But if one of these endpoints is open and the other one is closed, even though it appears on your graph that you have 2 points at that x value, this one doesn't have a y value that goes with that x value, but this one does, so it could still be a function. So things can be discontinuous and still be functions. You have to pay close attention to the endpoints. Okay? Good question. All right, domain. What's the domain? Okay, good. All real numbers, the domains are talking about the x's. Okay, so all real numbers. Why? Well, there's two ways to look at it. Algebraically, look right here at the domain restrictions. Is there any x value you're not allowed to plug in? No, if it's an x that's smaller than 1, you're plugging it in right here, right? If it's an x that's equal to 1, bigger than 1, but smaller than 4, it gets plugged in right here. If it's an x that's bigger than or equal to 4, it gets plugged in right here. But that includes every possible x value you could come up with. Also, look at the graph. From left to right, if you travel along the x-axis, could you ever find a point and you say, this x, it doesn't have a y value to go with it? Can you do that here? No. If you say that x, I'm going to say, guess what? It does have a y value. There's a point on the graph right here that has a y value that matches with that x value. Okay? What if I go over here? Yep. Somewhere down here, there's a point on the graph. Okay? And that x value has a matching y value. So every x value has some point on the graph where it's an ordered pair with another y value. So I know that all real numbers are there. Okay? My friend is a Jay-Z fan. She's like a teacher. And she literally has like a Jay-Z puppet and a Spider-Man puppet. And when she's talking about domain and range, she's like, domain, think about Jay-Z traveling across the stage. Are there any holes? Is he ever going to fall off? Like, no, he can just keep on going. Okay? He can just keep on going. And then Spider-Man is what she uses to talk about the range. Because what does Spider-Man do? He like climbs buildings, right? Okay. So our range, we're looking at our y values now, are up and down on our graph. If Spider-Man was climbing up and down this, he could keep going down forever, right? There's no gaps. There's no place he hits where it doesn't go any further. But if he's climbing up, he hits this, and then it goes back here, and then it stays here. So this seems to be the highest peak that they would ever hit. So how do we say that in terms of the range? The y values hit a maximum. So what do we say? All the y values are what? Good. And we're actually going to include equal to also because it actually hits that point closed and includes it. So y values are less than or equal to 3. Okay? Any questions about this? Okay. Yes? Mm-hmm. Uh-huh. That would not be okay because that means like 3.9 is part of the range, but it's not, right? So that's why the ones that are not included, we use that open circle because like what number is right before 3 or 4 or anything? Like we actually don't know, right? There's infinitely many in there. All right, I want you to make a note on your paper right now because we're going to also use a new notation. So this just means all real numbers. If you didn't know that, just write it next to it. This is what you guys are used to writing inequalities when you're trying to explain something's bigger than or less than or in between two values. You guys are used to seeing that kind of notation. We're going to include next to it something that we call interval notation. Okay? You're saying the same thing in a new way. So an interval means you're literally going to tell me, here's the number where it starts. Here's the number where it ends. Okay? If you use a mark like this, that means it's not included, meaning it cannot equal that value. If you use a mark like this, that means the value is included or is part of something that it can equal. Okay? So for example, let's actually start with the range because it's easier when we have something. You want y to be all numbers that are less than or equal to 3. Okay? Starts and ends from least to greatest. So what's the smallest number y can be? If y is all numbers less than or equal to 3, what is the absolute smallest number y can be? Yes? No? Negative infinity. Good. Okay, a little bit tricky. There's not actually a number it can reach. Because it can be any number smaller than or equal to 3. So if you say, oh, negative 10 is the smallest, I'm like, nope, there are smaller numbers, right? And that could go on forever. So for the smallest number, if it has no limit and it can keep getting smaller, we say infinite or infinity, and we put a negative in front of it to indicate on the negative side. So it's infinitely small. Then we have to decide, does negative infinity get one of these parentheses or one of these brackets next to it? Can you ever physically reach the number negative infinity? No. Okay? So since I can't physically reach it, I can't be equal to it, which means I have to use the one that indicates I'm not equal to it. Okay? So that would be this. So I'm telling somebody it can go forever small, okay, towards negative infinity, and then I want to tell them the maximum value of our range. What is the maximum value of our range according to our inequality? 3, okay? And then by the bracket that I put, I'm indicating whether they can actually get to 3 or they just go right up to 3. Sorry, other way around. So if it's equal to, I include 3 here. If I can't equal 3, I would put a parenthesis. Does our graph reach 3, or does our inequality say our y values could equal 3? Yes. So kind of weird, but do you see why people like it? It's like really small and like super concise and lets you know what's going on. Does anybody have any idea then how we would mark it for all real numbers? Yeah. Good. So it's going to have infinity signs on both ends because it's everything. So it can go from negative infinity to positive infinity, and because we don't physically reach those numbers, they would both be closed in by parentheses and not brackets. Okay? Yes?
Say they're both closed by parentheses.
Uh-huh.
How can you tell the difference between that and say what is
So the context in which you're using it. So if somebody says graph the point or find an intercept, something that refers to a point, then you know that. So you have to know the context of the problem. If someone just threw 2 numbers with parentheses around them on a piece of paper, you now have a question. Are you asking me to graph a point, or are you telling me something about a function? And hopefully the context of the problem would describe it. Okay? Is everybody okay with this? All right, so our goal